Hi all, back for another round of physics. And today I thought, well, we'll spend a little bit of time talking about this r hat vector. So a video or two ago, we were dealing with Newton's law of gravity. So let me go ahead and put that up there. And we went through and just discussed what the meaning of each of these pieces were in terms of the masses or the relative position vector, this r12 and r hat. And I thought that this short video today will just be dealing with getting a better sense of this r hat vector and this r12. Now, of course, you've seen the r hat vectors, or you've seen the hat notation before in terms of unit vectors, and just a little bit more practice on how to do this algebraically. So let's go ahead and close that out. Let's get this problem up. So here's the problem I've prepared for you. 3 masses, and it gives you the mass m at 3m and m question mark. So the m question mark, we don't know exactly what that mass actually is. But we have the other two. We have one that's 3 times 10 to the 5th, and excuse me, this should have a kg in it, kg right there. And then this one's 3 times the mass, and then this one we don't know about. And are located at different locations in space. So the first mass is at 1, 2, 0. Second mass, the 3m mass, is at -1, 0, and -1. And the unknown mass is at 1, 2, -1. Okay. And then we're asked a question. What is the gravitational force on mass m, so the first mass, due to the 3m mass? Okay. So the first thing that we should probably do here is we need to figure out this r vector, this r12. Okay. We need to come up with some sort of expression for that. And since we're having this problem going on, one of the things I would encourage you to do is take a minute and see if you can draw a picture that just kind of gives those positions of those masses in space. So go ahead, try to do that real fast. Pause the video. Okay. So you got that taken care of. Let's go ahead. I've got one myself here. Boom. Now, of course, we have to be careful. It's always difficult to kind of conceptualize and draw in 3 dimensions and that kind of thing. So you see, try to indicate that it's into the page. I've used these dashed lines that are parallel to the z-axis to kind of produce that into the page kind of feeling. But yeah, admittedly, it gets a little bit hard to actually visualize these things. Part of the reason I tell you to do this, though, is that it will help you with the directions later. It will help ferment things in your mind. Eventually, you'll get problems where it's not very easy to visualize at all. But if you kind of trust the mechanics and that it's working okay, you kind of build this familiarity with how to approach it, then you'll be fine. So let's get at it. We want to know the gravitational force of this guy acting on this one due to this 3m1. So you can tell that m's up here and 3m's back into the page a little bit more. So first off, let us see if we can figure out the vector that points from the 3m mass to the m mass. Okay, so we want, I'll go ahead and draw this in, although it might be a little bit sloppy. It might ruin our figure here. We have one vector that points from the origin to the 3m mass. Okay, that's our r3m. We have a second one that points from the origin to this mass. That's our rm. And we want the vector that points from here to there. So let's go at it. Our starting position is the 3m mass. So I'll write down, okay, well, r12. In this case, it starts from the 3m mass and we want it to end up on rm. So sometimes I still think of this as final minus initial. Final minus initial, keeping in mind that now we're dealing with 2 objects in a single time. Okay, so usually when you're thinking final minus initial, you might be thinking of this delta r. That's not what I want you to be thinking about here. Delta r means one object at 2 times. Here we're talking about 2 objects at a single time. Okay, so the relative position vector. So that's why I put the quotes in. Rather, you should think of where you say the head of arrow, and tail of arrow. So if you think about that, if you think of it in that sense, then R12 is simply the position of mass m minus the position of 3m. Alternatively, rather than thinking of that way, this is R12, you could think of it as saying, hey, wait a minute. If I take this relative position vector and add to it the position of mass 3m, I should end up at the position of mass m. Okay, so you could kind of flip it around if that helps you a little bit. Well, we're off and running like a herd of turtles here. We know that we have algebraic expressions for both of these, right? Those are given in the problem. We have 1, 2, 0. Excuse me, it's a bale of turtles, not a herd of turtles. Minus, and then we have negative 1, 0, 1. Excuse me, negative 1. So altogether, we have 1 minus, okay, so we have 2, 2, 1. And of course, our units here are meters. So there is our expression. And what I'm going to do is I'm just going to move that piece. We'll move it right over here. There is our expression for the position of the single mass with respect to the 3m mass. Good? Now we're not done, of course. So we're asked for the gravitational force. So that's just step 1. We've just figured out how those two are the relative position. Now we've got 2 more pieces of information we need to calculate. The first one is we notice that R12, if I show this and get rid of that for a second, we notice that R12, it's a magnitude and it's squared. So we better find the magnitude of this vector. So that's the second step. Let's go ahead and get that rolling. So we need, I'll put here the magnitude of this. Okay. So we have to remind ourselves, how do we get the magnitude of a vector? You take the individual components, square them, and add them together. Okay. Now, how I usually like to think about it is, let's go ahead. What I'll do is I'll take the dot product of the 2 vectors and then simply take the square root. That's just a more compact way of thinking about it, but I'll tell you right now, that kind of way of thinking will be helpful in the future. So right now, if you think of the sum of the squares of the components, that's fine. This is kind of a more generic version of that, and it'll help. That comes up again. So we'll go ahead. The dot product, that means that I have 4 plus 1, and I square root. You say, well, that's convenient, Greg. That means that the magnitude is just simply 3. Rather convenient. Okay. So we've got our second piece of information here that we need. So I'll go ahead and box that in. Yay. Of course, you probably already had that. You guys work a lot faster than I do. So there's the second piece of information. Okay. Now, of course, the third piece that we need to get at is this. We also have the r hat vector. So we better go ahead and calculate that out. So for the r hat vector, so we go r hat, and we remind ourselves of color change. Let's go ahead and get that color in there. So we remind ourselves that for the r hat vector, say, how do you calculate a unit vector? You take the regular vector, say r, I'll call this 1, 2, and you divide by the magnitude of that vector. So you've already got the pieces that we need here, right? We've got the regular vector, found that. We've got the magnitude. So now we just need to take those two pieces and plug them in here. So we get something that says r hat is simply 1 over 3, there's our magnitude, times 2, 2, 1. And we go ahead and multiply that through. We get r hat equals 2/3, I'll express it like this, 2/3, 1/3. And of course, the unit vector, the units of a unit vector are nothing. You can see that up here. You have r, which is in meters, and you're dividing by meters. That means that the unit vector is unitless. Okay? So you have to be careful there. Now this unit vector, we've got it. It's the direction from the 3m mass to the 1m mass. Okay. So the last thing that we should probably think about here, so I'll go ahead and circle that. Finally got my squares and lines figured out. The last thing that we should think about here, move that over here, is what does this negative sign mean? So I've got this negative sign here, right here. So thinking about that negative sign and looking at the picture, the r hat vector points from 3m to m. And we already determined that. This is also why sometimes a picture does help out. That means that the negative, that's, if I put a negative sign in here, that vector points from m to 3m. The negative sign flips the direction of that vector. That's why we tend to think about the signs going with the directions. You'll hear that a lot, that the sign, the negative sign, or I'll say signs go with direction. You might hear that a lot. That's just when you're dealing with some vector quantity, oftentimes you'll see people thinking about the sign, the negative sign, going with the direction, which is why I also grouped it right here, right? I grouped the sign with the direction. So once you have the direction, r hat, you know that the sign flips that to the other way. Well, let us actually go ahead and I will get rid of this. And I'm going to go ahead and grab this now. And now we're in a position where we can actually apply this. We'll go ahead and move that so that we can see it. And let's go ahead and run this sucker, since we're asked to find the gravitational force. So we have Fg equals, well, gravitational constant. Okay, so we have a value for m. So let's go ahead and now plug in our values. 6.67 times 10 to the negative 11th. And we have 3 times 10 to the 5th. And we have 9 times 10 to the 5th. That whole rigmarole is divided by, well, our magnitude is 3, so magnitude squared is 9. So we'll put 3 squared. And then we have this negative r hat out here. Negative 2/3, negative 2/3, negative 1/3, where I've actually incorporated that negative sign into the expression. Now we run it. Well, 3 squared, get rid of the 9. That's nice. And in fact, you see that, oh goody goody, we have a 3, we have a 3, 3, 3. not by accident. And so we end up with something that says the force of gravity. Oh, I guess I forgot to cancel out. Let's see. 10 to the 5th, 10 to the 5th. So if I cancel these guys out, this just gives me 10 to the negative 1. Right? I have 10 to the negative 11th plus 5 plus 5. So at the end of the day, if I keep writing this, I get something that says 10 to the negative 1. So I get 0.667 times negative 2, comma, negative 1. And of course, at the end of the day, this whole thing's in newtons. So that's good enough. There's our final answer. That's good enough. Now, of course, if you want to go ahead and multiply through more and express it just as a unit, or if you want to express it some other way, that's fine. But this is all we really need to do. So, good. Now, I guess the last thing I'll say, well, let's go ahead and think about how we actually did this. To actually get f of g, what we did was, step 1 was we found the relative position vector. So we found this. Then we found the magnitude of that relative position vector, r1, 2. The third step was then finding the r hat. And then finally 4 is run the problem. Run, run, run. Okay. So just a summary of what we did there. Now, since it was not specified, let's go ahead and look at one more thing here. And I'll go ahead and get rid of this stuff. Wrong layer. There's one more thing I thought that maybe we should look at real fast. And the question is this. If I can find, excuse me, I got to find the right layers here. There we are. Excuse me. Sorry about that. The question is this. If I actually look at this problem, the second question that I would have for you is what value of m question mark? So thinking about this unknown mass, what value must that mass have such that Fg net equals 0? So if I think about this m mass, the question I have for you is what value of m question mark such that the net gravitational force on m is 0? So go ahead, take a minute, think about that. Okay. And here's sometimes where the picture really helps us out. Okay. If we see the question really is this question mark mass, this unknown mass right here, is it in line with the other two masses? Because really, remember, that's not right, excuse me. That looks better. Remember, gravity is attractive. And acts in line of, I don't know, acts in line. I guess I'll just say it acts in a line. So the idea is that gravity acts along this blue arrow from 3m, kind of inwards and downwards, whereas gravity for the second one will act in this direction, right? So you can just visually see that if I take these two vectors, it's an ugly vector, if I take these two vectors and I add them together, you can just visually see that, hey, there's no way to get those two things to cancel. right? They're not along the same line. There's no way that I'll actually get those two to cancel out. And so at least the idea here is there's no such mass, no such mass possible. And that's one where the picture really helps you out. Now, if you wanted to go and try to find it, you certainly could. We have an expression for the gravitational force due to that pair. And you have a way of actually finding an expression for the gravitational force between these two pairs. In fact, I encourage you, go ahead and try that out. Find the r vector, find the magnitude, find the unit vector. But you'll find that it doesn't matter. There's no possible way to actually do it. Okay. So we already know the answer. In fact, take a minute. Why don't you take a minute, just pause the video, see if you can come up with that. Show that the r hat vectors are not in the same direction. Okay, you got it? Well, it's good. It's always a good practice. Let's go ahead. We'll say r, and maybe here I'll just call it m in question mark. Okay, I want it to end on my mass m, and I want it to start from my question mark mass. So I'll do that. Of course, this is 1, 2, 0, minus 1, 2, -1. And so I get something that says, okay, well, it should be 0, 0, oh, that's nice. Well, that's rather nice. Which means you can see right away the magnitude of this vector, m question mark, is equal to 1. Right? And might as well just go ahead and write it out. The gravitational force between these is just going to be our g m1 m question mark, and it will be in the negative z hat direction, -1. So as I already said, there's no way for this force, I'll call this m question mark, there's no way for this force to cancel out the other force. You see, there's no x components, there's no y components, whereas our previous answer had those. So there's just no way for it to happen. Okay. Well, I'll stop it there for right now. Just a quick run through on Newton's laws and specifically focusing on these r vectors and r hat vectors. But hey, next one we'll just deal with some more physics, probably some circular motion, and then we'll continue on to work. Thanks for your attention. Have a good afternoon.